Alright, so this section is going to be a little different. Little bit of practice. I'm not going to solving. What if we just want to know what type of solution we have? So we do have infinite many solutions, one solution, or no solution. Is there a way to know without actually having to go through the Gauss-Jordan elimination method and solving and finding it at the end? Okay? That's pretty much what this section is all about. Okay? So we're going to talk about independent and dependent variables much more in this section and eventually going forward. So let's just go back a little bit. So we were given an n by n linear system with an augmented matrix. So remember what this represents, right? So in general, if we have m equations with n variables, it's going to kind of look like this. Right, so this is our portion, and then its respective augmenter matrix will look like this. Right, so now we're talking about this type of situation. Right, we have an arbitrary n by n matrix where they're not the same for now. Okay. All right, so if this is the case, we have a couple situations happening. So the solution represents by the matrix CD, so its augmented matrix is inconsistent, basically no solution. If and only if this augmented matrix has a row of this type of form, and any one. It could be multiple, but as long as it has one of them, we say it's inconsistent or no solution, right? The fancy way for saying it. Every variable corresponding to a leading one in its matrix is a dependent variable, and that's a key thing. Okay. Let R denote the number of non-zero rows in this augmented matrix. Then, so again, R is the number of non-zero rows. Okay, so basically, not this part, right? Just a bunch of zeros. So a bunch of zeros, so non-zero rows, so it has numbers in them. Then R is less than or equal to n plus 1, meaning the number of non-zero rows is less than or equal to the number of columns plus 1. That's a little bit of a key later on. And then the last one, let R denote the number of non-zero rows, just like above. If the system represented by the augmented matrix is consistent, meaning we actually have a solution, then R is less than or equal to n, not n plus 1. Okay. All right. So let's figure out what these definitions actually mean. Okay. So let's consider this augmented matrix here. Alright, so let's see what these actually mean. Okay. So let's write down what we have. So we have x1 equals minus 2x2 minus 3x to the fourth, right? We have 1, 2, 3, 4, 5, 6 variables. Minus 4x to the 6 plus 1. x3 represents 2 minus 2x to the 4 minus 3x6. And finally x5 is equal to 2 minus x6. Okay, so we have a total of how many, well, in this case n represents the, n by n, so let's go by this. We have a what by what? We have a 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6. Oh, rows by column, sorry. 6 by 5. Oh, sorry, no. Forgetting you. I was right the first time. Rows go first. We have 5 by 6. So therefore, if it's a m by n, we have n equaling 6 this time. Okay. And then r will always represent the number of non-zero rows. So non-zero rows, right? So rows go this way. We have 1, 2, 3. And it checks out, right? So 3 is less than or equal to 6. So both will work. And the interesting part is, and we'll talk about that actually in a little bit, is how many dependent variables we actually have. Well, we have 3. So we have 3 dependent variables. So interesting that they're this exact same r value, huh? Well, it's not really sometimes a coincidence itself. So let's C be the augmented matrix such that it's an m by n plus 1, and this represents the augmented matrix, right? So this is the n plus n by 1. This plus 1 is the answers to the b's, the b1, b2, b3, right? That's what that represents. Matrix in reduced row echelon form, where the augmented matrix represents a consistent system. So we actually have a answer. That's a key thing. Okay? A lot of these can be with answers. So let the augmented matrix have r non-zero rows. Then r is less than or equal to n, which we found that's true. And in the solution of the system, there are n by r variables that can be assigned as arbitrary values, independent variables. And that's the key thing. Which means r represents the number of dependent variables. Okay. So, little recap. Because of this theorem, which is also pretty important, we have 3 possible outcomes we can have for a system. The system is consistent, meaning no solution, which makes sense. The system is consistent, meaning we have a solution, r is less than n, and there are n minus r independent variables. Therefore, we have infinite many solutions. Or number 3 is the one we've been doing. The system is consistent, which means it has a solution, and r equals n. Now, when does that happen? When we actually have a unique solution, right? Because it would make sense because they're all independent of each other, right? We don't have any independent variables. Okay, so now we can figure out, what situation we're actually in based off just the r and the n values. Okay. Now, before we go to an example, there's a nice little query to talk about this. So consider an n by n matrix system of linear equations. If m is less than n, like it was here, right? M is less than n. Then either the system is no solution or infinitely many solutions, and that's the key thing. So we can already cut this into just 2 of them based off one very special thing. Okay. Alright, so let's try this out. Here's an interesting example. So given a 4 by 5 system of linear equations, so this is m and this is n, what are the possibilities for the solution set? If the system is consistent, what are the possible number of independent variables? Okay, So first off, what are the possibilities of the solution set? So one, we could have no solution. So we can have either consistent or inconsistent. That's it. Now, why is that? Why can't we have a unique one? Well, it follows this corollary, right? M is less than M, so 4 is less than 5. So based off this corollary, it's either going to be inconsistent or, in this case, infinite many solutions. It's consistent, right? Okay. So now, if it's consistent, which is in this case going to be this situation, what are the possible number of independent variables? Now remember, this means we have infinite many solutions. So we're now in this 2 right here. So therefore R is less than N. And in this case, N is 5, so we know R is less than 5, right, for some arbitrary portion. I don't know what R is, but I do know it has to be less than 5, right? So what can we have? So R could be 1, 2, 3, or 4. Okay, so if we're talking about independent variables, so the number of independent variables follows this pattern. So we can have 5 minus 1, which is 4. We can have 5 minus 2, which is 3. 5 minus 3, which is 2. And then finally 5 minus 4, which is 1. So this is the possible of number of independent variables based off the value of R. That could happen. So a pretty interesting example, more theoretical than actual applications itself. Okay. So let's try a similar one. What are the possible solution sets for the 3x4 system? And here's our system. Okay. Now, just like the corollary above, we have M is less than N, right? 3 is less than 4. So based off this corollary, we have one or the other, right? But this is what are the all possible solutions we can have. So now, this one is a bit of a tricky one because they're equal to 0, right? So we have something called, well, I don't like what it's called, but it's something called a trivial solution. And the trivial solution basically says they all equal 0, which makes sense, right? If I plug in 0 for every single variable, it's guaranteed to be 0. That's why it's called the trivial solution. So it's kind of like, okay, sure, that makes sense, right? So it's not so fun. Okay. The second situation was, well, if it's consistent, we have infinite many solutions. And we're done. Interesting one, right? Again, a little bit more theoretical section than what you may think. Okay. All right. Last little definition down here. So, well, not last one, but a couple one. If, however, we have this situation happening. So if it are all equal to 0, we have a very special definition. We'll be using this a lot. So if the linear system is all equal to 0, this was called a homogeneous system. Okay, and if you take in again a little bit of differential equations, this might be a little bit reminder of your homogeneous systems and all that fun stuff. It follows the same pattern. So anything that's equal to zeros, so all of them, not just the one, but it has to be all of them, that's called a homogeneous system. Now, the interesting part about a homogeneous system is you either have one of these two. So a homogeneous system is always consistent, meaning it always has a solution set. Okay, we can either have the trivial one, which again I don't like what it's called, but it basically makes sense, right? They're all equal to zero. Okay, so trivial solution set, or all have non-trivial solutions. We actually have a different type of solutions for them. Okay, so it just depends on what we actually need and what we get. But the most obvious one is just going to be all equal to zero. Okay. Okay. So, nice theorem here as well. So a homogeneous system of linear equations always has infinitely many solutions when m is less than n, and that's a nice one. Okay. And remember, what it means by non-trivial means they don't equal just zero, right? That's what they mean. So let's put it to the test. So what do we have here? So we actually have a 3 by 3 here, right? So let's see if we can make this theorem fail, right? So based off this theorem, these are equal to each other, so which means we wouldn't have infinitely many solutions. We actually will have one trivial solution, or in other words, we should just get this. Because that's the only possible ways we can happen. It's either infinite many or the trivial one. So let's prove that we actually get the trivial one. Alright, so this is kind of nice. These twos go away a lot, right? So I'm going to do R2 plus R3. And I'll keep R1 the same. And I'll replace row 2, so this minus this gives you 0. This gives you 4, this gives you 11, and there's a 0 there. And now I'll replace row 2 with the same process. I'll do row 1 plus row 2. Alright. So it looks like I can get these out of the way, so I'll put row 1 minus row 3. And then so I'll keep this the same. So this minus this, that minus that, and that minus that gives me that. Okay. Alright, let me get rid of these. So multiply this by -2. So I'm going to do row 3 minus 2 times row 2. So if I multiply this by 2, it would be 0, -2, oh, just 2. And then 8, and 0. Keep everything else the same. So I'm going to do row 3 minus row 2. So this minus this. This. Oh, this is a 4, sorry. Multiplied by 2. So this minus this. This minus this. Alright, and we're almost done. Just one more row to finish up. So I can multiply this by 3. So I'll do row 1 minus 3 times row 3. Okay, and this 4 and 3 aren't very fun to do with, so I'm just going to break them down, you'll see. So I'm going to do 1/2 times row 2, and I'm going to do 1/3 times row 3. Oh, and I can also do the same thing here, so I'll divide row 1 by 1/2 as well. So it looks like we're on the right track. x1 is 0 already. And so is x3. So we just got to show that x2 equals 0, and we got our pretty much proof down there, which is not bad, right? So now we're just going to have to multiply. So row 2 minus 2 times row 1, or sorry, row 3, and we get our final answer. And there we go. So the only unique solution is our trivial solution, which is just they all equal 0. And again, this works because it's a 3 by 3, so m equals n, which is no fun, right? That's not fun. The fun ones are that ones, right? How do we do that kind of situations? Okay, so let's try one like this. So for a system of equations, determine the conditions of A, B, and C in which makes the system consistent. Alright, so consistent meaning we actually have a solution, right? So, a little theoretical, but we could do this, right? So, we have to find what the answers make this true. Alright, so this is a 3 by 3 again. And we don't know if it's homogeneous, right? These are arbitrary values, so this thing probably won't apply anymore. Okay, so let's see. Okay, so looks like
attention students, session.
So it looks like I just subtract these around, so that's what I'll do. So I'll do row 1 plus row 3, and you know what, just for fun, I'll put the result in row 1. So I'm just going to add this to this, so that gives me 0, that gives me -1, -3, and then I'm also adding these up, so it'll be A plus C, because I don't know what they actually are, right? So I gotta keep them as arbitrary values. Okay. Alright, next up, get rid of this 2, so I'm going to multiply the bottom by 2. And then I'll do row 2 minus 2 times row 3, because that's what I'm about to do. And I'll keep row 3 the same. Okay. Alright, so it'll be this minus this, this minus this, this minus this, and this minus this. Alright, looks like we're almost done here, right? We got at least one whole column done and a little bit of the second column done. And this is even nicer because these actually go away. So all I'm going to do now is do row 1 plus row 2. And I'll keep the middle one the same. So I'll replace the first row. So remember I'm adding, so row 1 plus row 2, these together, so 0 plus 0, 0, 0, and adding these up gives you A plus C plus B minus 2C. Okay, so that goes there. I'm going to add a space. Okay, so let's rearrange this to make it more proper to look at. So I'll move this up to be the first row, this to be the middle row still, and then the bottom row this gives me minus C when you add them. Now remember, if I want this to be consistent, that means I can't have this being a number, right? That means it's no solution. So what this represents is this entire bottom row must be zeros. So that means we must have the condition that this sum and subtraction must equal 0. And that's our condition. So those are the conditions A, B, and C that must be true to make this consistent. Alright. Now, the interesting part about system of equations, and I told you we're only doing linear equations, but they are unique ways of saying these are linear equations. Okay, so there's other types of, and again I put in quotes, linear systems based off matrices, and that goes into conic and surfaces, or in other words, geometry. Okay. So the question is, what is? Oh, sorry. So the question now becomes, well, how does a conic and a surface equations being linear? It doesn't make sense. We have x squareds, y squareds, even cubes when it comes to surfaces. Well, we go around that by saying, well, the coefficients is what makes it linear. That's the key thing. Okay, so when we came to our line, we were solving for x, right? For all these arbitrary x values when it comes to it. Now, to make this a linear system, we're going to be solving for the coefficients in front of the variables, not the variables themselves. Right? There's always a catch, right, when it comes to it. Okay. So here are the general equations for a quadratic and a surface, respectively. Okay. But let's go down 1 degree. Let's go just to a line for practice sake. So let's do this example. Find the equation of a line passing through the points 1, 2, and 3, 7. The general equation is ax plus by plus c equals 0. Now, we could do this the old-fashioned way, right? Find the slope, plug it out in, and you find it. But how do we do this, the linear equation, linear process, right? Because that way you could see how, things are done in actual computers. So remember, knowing that A, B, and C is the coefficients, right? So that's what we're looking for. Okay? So how this works is we're going to just plug in what we have. Okay? So if these are the variables, maybe it's easier if I do this. So if those are the variables, I'm going to plug in x, y in each case. So if x and y are 2 and 1, that means I'm going to have 1 times a plus 2 times y plus c equals 0. And then for the other one, I'm going to have 3 times a plus 7 times y plus c equals 0. Okay. Now, what does that mean? See if this focuses. There we go. So now when I want to write this in our matrix, again, oh, sorry, this is supposed to be a B here, not a Y. I put in B. So now, 1, 2, 3, 7, and the 1 in front of the C is what we put in the matrix, not A, B, and C. Okay, so I'm going to have 1, 2, 1, 3, 7, 1, and these all equal 0. So a homogeneous system. And now at this point we just solve, which shouldn't be too bad, right? So I'm going to do row 3 minus 3 times row 1. I'll keep row 1 the same. So this minus this minus this, and this minus this. Okay. So now I'll do row 1 minus 2 times row 2. So we have, okay, subtract this minus this minus this minus, so it becomes plus, so it's 5 there. Okay, so now from here we go backwards, right? So remember, this is going to be A, B, and C. So we have A plus 5c equals 0, and we have b minus 2c equals 0. So we have a is equal to negative 5c, and b is equal to 2c. Okay. So now if I plug these two back into our equation, so everything is now in terms of c, I'm going to have negative 5cx, right? I'm putting these letters into a, b, and c only, plus 2cy plus c equals 0. Okay. Now notice they all have c in common, so if I just divide it out and just get rid of it, we get exactly what we want. And there's our equation of a line. They may think this is, a super long way of solving for an equation of a line, right? But yes, it is, right? But remember, the whole point is now we could do stuff like this using the exact same process. Okay. Now, let's do a little harder example from this, okay? So, all we want to do now is just going to find the augmented matrix for the conic section passing through the points here. Now, again, remember, these are the x and y. So our conic, since we're doing a conic surface, is right here. Oh, general surface, right? Yeah. Oh, right here, sorry. Okay. Okay. Now, how do we do this matrix? Well, it's going to be the same thing we did here. So I'm going to do an example so you can see how does it go. So remember, we're solving for a, so I'm just going to plug in each one respectively. So if I plug in negative 1, 0 for the first point, if I plug in negative 1, 0 in for x and y respectively, so This is going to be negative 1 squared just gives you 1, so it's be 1 times a. I plug in 0 and negative 1 for x and y. That just gives me 0. So 0b. Next one is y squared, so 0 squared is just 0, so it'll be 0c. Plug in negative 1 for x, it gives me negative d, or negative 1d. Plug in 0 for y, that gives me 0e. And then finally f is by itself. So that is going to be our first equation. So we have to do for each individual point. So we have to do this 1, 2, 3, 4 more times off this. And just like we did here, right? We had 2 here. So now, in our augmented matrix, the first row is going to be exactly this. The coefficients in front of A, B, C, D, F, G. Well, not G, but all the way to F. So 1, 0, 0, negative 1, 0, and there's a 1, and this all equals 0. And this always equals 0 because there's always a 0 there. Okay. So again, we'll just do that for every single point. So again, if you plug in now 0, comma 1, so x is 0 and y is 1, you will get this out. Now if you plug in 2, 2, things drastically change. Now we have multiple coefficients. Well, f is always going to be 1, so I'll just put 1, 1 there. Okay. Same thing, if you plug in now 2, negative 1, for when x is 2 and y is negative 1, we should get something a little similar to it. And then finally, when you plug in 0, negative 3, so x is 0 and y is negative 3, we will eventually get this. Now, the same thing as we did above, we can solve for this matrix and find what the coefficients will be here and actually get an equation. If you know want. But this time now computers do this, and that's what they were made for, to generate this kind of stuff much, much faster than what we can.